Hello and welcome everyone. Long time no see. So we're gonna be solving this problem, which is a tree DP problem, kind of. Pretty cool one. Now look, in this problem, the problem name is Parsas Humongous tree. Basically, in this problem, you're gonna be given a tree. As you know, in a tree there are n-1 vertices and n-1 edges and n vertices all together, combining with only one component. That's what tree is all about in a graph. Now, in that tree, for each and every node, you'll be given two values like that. Okay, for each and every node, you're going to be given two values, L and R. Now, at the end of the day, what you have to find out is you have to find out the maximum possible beauty of the tree. Now, how would you measure the beauty of a tree? The beauty of a tree for each and every edge can be defined as, let's say for this edge, you can take any of those values. For each and every vertices, you can take any of those values, and then absolute values of any particular edge, you would calculate the absolute value of the chosen respective value for each and every vertices. Now, this value could be either the left one or the right one. That's up to you. But what you have to find out is, at the end of the day, you have to find out the maximum number of those values, and some of those absolute values, values of the n-1 edges. For example purpose, let's take this example. This is a pretty easy one. I will dive into deeper, also explaining why we need DP inside this problem and why greedy solution. There's also a greedy technique that we need. Now, also one thing to notice is that between L and R, I can take values between L and R. Okay, I can take values between L and R for each and every node, but the real thing is that we don't actually need any values inside those two L and R. We only need the boundary ones, the L or the R value. This was the greedy one, because it's pretty intuitive that if you take either the two boundary ones, not taking in between value, if you take either the boundary ones, it will definitely ultimately result something which is which will deliver maximum possible something values, not by not taking in between values. I hope you get that. So we are only considering the edges, which is either the left one or the right one for each and every node. Okay, so let's say for this two nodes, where one node is 1 and 2, and their respective two values are 1, 6 and 3, 8. Now, how many possible ways that you can make? You can either take 1 from this value and then 3, and the absolute value would become 2, and you could either take 1 and 8, absolute value would become 7. You could either take 6 and 3, absolute value would become what? 3. So out of all these possible values, what is actually the answer? Maximum one is definitely 7. That's why it's 7. Similarly, for this case, if we take 1 and 5, 1. If we take, okay, the values are 1, 5, 9. Okay, so think about it. If we take 6 minus 1, then I can say that I have 5. And if I take for this edge, as I've already, okay, one thing to notice, it's also dependent on which values you take. If you take any values to account, you will not use another values in the next edge. Let's say for a particular vertices, you've chosen some values. Now, if you want to make or try to find out the beauty, you would always have to remain with the same values for that particular vertices of one possibilities that might make the ultimate result. That's why if you have taken 6 for any particular combination, if you have taken 6 for this value, it will always remain 6, irrespective of whatever edges you get. Okay, it's going to be dependent like that. Now, if you have taken 6 for this edge, you would also have to count 6, because it's obvious this node is dependent on these two. This node has two childs like that, so you cannot take for one value of this edge and the other value of the other edge. No, it's not possible. So that's why 1 and 6, if I take 1 and 6 now for this edge, then for this edge it would seem that I can take, instead of taking 7, why shouldn't I take 9? Now if I take 9 here, then 9 minus 6 becomes what? 5, 6, 7, 8. 9 minus 6 is 3. 3 plus 5 is 8. So actually, basically, this is actually the maximum one that's gonna come around. And yeah, that's also, I'm gonna explain this case. Okay, now how is this? So in order to jump into the DP solution or the DP solution, I would like to say that there is a greedy approach that I've already talked about, is that we are only considering the boundary two numbers, which is the Li and the Ri. Why is that? I've told you it's pretty intuitive. If you take each and only the boundary values, by not taking the in-between values, it will seemingly result out of something maximum. So that type of greedy intuitive mind you need to have. Now we're gonna jump into and say that why we need DP for this problem. Because what you have is, what are the choices that you need to have? First of all, you need to traverse the whole tree. That's the number one condition. So in order to traverse the whole tree, you need to traverse each and every node at least once, for sure. Now, for each and every node you need to traverse, but also not as there are two possibilities of values that I have to take for each and every node. Like for each and every node I have L and R, right? That's why for each and every edge I have two possibilities. For each and every edge I have two possibilities that I have to take account. Not one possibility, it's two possibilities. I'm telling you once again, because just think about it. Normally when you do DFS, what do? You just traverse from the root node and then traverse each node and each edge only by once. But here, you have to traverse each and every edge twice, at most twice, okay? Twice, which is for if you take for this node's L value, or if you take this node's R value. Okay, so these are the two possibilities. Now, when I say this is statement, what does that actually mean? What does that actually mean? I'm taking for each and every edge two possible edges. For each and every edge, two possible values that I can take. I have the option to take for two of the different possible edges, but I'm going into the same node. Okay, so for each and every node, for each and every edge, I have two possible ways that I can go forward. Either I will take account like that. Let's say for each and every node I have two values, L and R. Now, if I take account L, then for the next child or any child I have, I can either take the R of that child or the L of that child, and I will try to find out the absolute value, and I will also see what is the maximum from this. Now, a node might have several different childs, just like this child, it might have several different childs. So what would you do for the rest of them? For the rest of them, you would also have to do the same thing, and then finally add these child's value. Why we need to add this child's value? Because they're child. Of course, you need to take account for each and every child in order to make the beauty maximum. And also, one thing to notice is that When you try to find out for each and every node, like if this is a parent and this is a child, okay, then I will initially consider that I have already figured out what values that I've taken for my parent node, and for my child node I have two other values that I can take in order to go forward. Okay, I hope I made you understand. Now look, for parent, I will always have the choice what I've taken previously in my parent. Okay, I've taken this value, L or R, any of those, doesn't matter. But for each and every child I have two other options, either go for L or go for R. Now either of them, if you take them account, you need to add the edges. Would you add the edges? You know, edges values, you know, how we did that, using the absolute value operation of the two values that I've chosen, L or R, any of them. And finally, similarly, for these two choices will be for each and every child. So for each and every child I have these two choices to make, and then for each and every child I'm gonna take the maximum result of their choices, and I'm gonna add those. It's obvious, it's definitely going to be needed because I have to find the maximum beauty value for the whole tree. There you go. Now the question is why we need DP. Look, that's why I've drawn this small little sketch here. Why we need. Now simply just imagine the tree as a straight line where there are only one edges like that, and you have nodes in between them. Now I've told you that if I want to get from this node to this node, I can either take this node's L value or this node's R value. So I have two other options. Remember, I will always know what I've taken for my parent. So I know that I have taken something for my parent. It doesn't matter, any value X, which could be L or R. Okay? This L and R is actually referring to this node's possible values that I can take. If I take that, where will I move forward? Now look, for L, I can go to this L, I can go to this L, L. Similarly, if I can also take this L, and after that I can also take this R, and then this L, and then this R, any of them. So ultimately, what is actually becoming? Look, for each and every edge, I have two possibilities. What does that refer? If you do a combinational operation or just simple combinatorics, you will see that there are a total of 2 to the power n combination for each and every edge, for the whole tree, for each and every nodes. So for each and every nodes, I'm taking two other values, the L and R. When I take those, I have two different possibilities. I mean, like a whole new sequence are creating. Total number of sequence could be 2 to the power n possible beauty values. Out of these 2 to the power n possible beauty values out of these 2 to the power n possible different combinations I have to make and output the maximum one. Now, you know that you cannot traverse that much of time in using because you have like time limit of just 1 second. So you have to come up with a solution. Yes, we can do that. We can just memorize the overlapping subproblems, and that's what we do. Now, you know, when you go for an optimization problem using DP. Now you can like convert this. You can convert this complexity 2 to the power n to n times 2. That's pretty easy. So ultimately, it's going to be dp of source meaning by for each and every node I have like two other options. I'll say that node, total number of nodes, and I have two other options. Now this values dp of any node of 0 meaning by I'm taking the L1 or I'm taking the R1. dp of, should I say dp of, like that, the dp of a source of either 0 or either 1. So converting this complexity to 2 times n is a really big of a job that we actually optimized. So that's what we're going to be doing, and we have converted that into a DP solution. Now what will be the transition of the DP? I will show you in the code part what it's going to be look like. Now let's take you to the code part here. And similarly, this problem is definitely like something going to be like that. Okay, for this example, you would see that you could take 17. I hope you get that. I hope you understood what I tried to say. You will understand that solution easily. How is this actually 62? And also the greedy solution that I've already talked about, the greedy approach, intuitive approach that you need in order to solve this DP problem. So basically it's a new type of DP, like you could call it as a tree DP, okay, in which we have like this something that we're going to be taking the test case, and then n, this is the DP1. For each and every node I will say that what will be the, okay, so I forgot to explain what is DP of source, DP of source of 0 or DP of source of 1. What does that refer? That refer is that if I take this node, if I start from this node, and if I take the value either L or R, what's the maximum beauty I can get from this node? Okay, when I traverse it in a DFS fashion. Okay, so for each and every node I will have the maximum beauty. Okay, so for each and every node like that, I will have the maximum beauty out of this, or out of this. So these are actually referring the DP of source of something, which is, or DP of source of 0 or 1 or whatever you say. Okay, now let's take a look at the code part here. We're taking the L and R. For initially we have to take that for each and every node's values, and then taking the graph tree, taking into account like that, and finally we're outputting the answer as the maximum of DFS of 0, minus 1, 0, and 0, minus 1, 1. What does that refer? Actually I'm taking the nodes as 0 base indexing, and minus 1 is actually referring that the node 0's parent is initially minus 1. And why I'm taking two maximum out of 2 possibilities? Because it's intuitive that I'm starting from a root node, so I would definitely have to take maximum of either if I take the left one or the right one, because my transition is actually moving from child to parent. That's why when I start DFS from some node, I have to take account for the left and the right both. You will understand more when I dive deep into the DFS function. Now let's go to the DFS function here. And inside that, this is the typical DP memorization part. You know it very well. Now here the basic DFS one. If the child is not equal to the parent, what we do? We generally do just the DFS operations. But here we're taking look, this is the fun part. We're taking what? We're taking it from child's perspective to the parent's perspective. I've already told you that when I start from some node, I will take account for both of those values. I'll take the possibilities for both of those values. Now look, inside the for loop, what I do, typical DFS, inside, this is the new part here. That's gonna, this is the transition part 2. What is the transition part? Look, this column is actually referring what is the node, what is the value that I've selected for the parent. Yes, I've selected 0, which means I've selected the L referring. Now if I've selected 0, then I know that this value is fixed, but my child's value is not fixed. That's why I'm taking either my child's left value or right value. When I take that, I also have to add the weight. What is the weight? Of course, we know how do we calculate the weight. We have calculated, we've taken a vector pair. Inside that vector pair, we've took account L and R, those two values, and then just taking the absolute value of the first one, and dot first is actually referring the L1, left one, and the right one is and second dot second is referring to the right one. for each and every node. And I hope you get that. This X is referring if I've taken the left value of my child or the right value of my child, what would be the output. And this, what is this doing? Result plus equal to maximum of x comma y. What is this referring? X and y, you know, the two possible values for the child that I can get the beauty. And why is this plus equal to? Result plus equal to. Why is this? Because any node can have more than one child too, because it's a tree. That's why for each and every child I have to take account and I have to add those beauties. That's obvious and intuitive. And finally, returning dp of source of a column, you could say color equal to result. That's how we did it. I hope I made you understand. Yeah, so till next time, goodbye.